All right, good morning everyone. So we will try to start our discussion where we have left. Let me Okay, so we were trying to wrap up case 5, which was our PID controller. Çok yaşayın.
Pardon hocam, mikrofonu çıkarmış, kusura bakmayın.
Rica ederim. And we what we started to write down was actually the, hold on a second, let me see. Okay, so we had actually we had written down GC of S, which was in this case composed of the 3 components, but after a while we arrived at the fact that this was actually resulting in 2 zeros, 2 separate zeros, and a standalone integrator, and with a separate gain. Okay, obviously this was actually composed of an expression like this. So in fact alpha and beta were in fact a combination of all the parameters of the actual parameters of the PID controller. Okay, so this was S squared plus 1 over tau d times S, and plus 1 over tau d times tau I. So the parameters of the numerator polynomial are actually a combination of the parameters of the controller. Okay, and then we arrived at these 2 separate zeros and a standalone integrator. Okay, 2 zeros and 1 pole in the open loop transfer function. Okay, so obviously these these zeros can be real or complex. Okay, zeros can be real or complex. Their exact values depend on all 3 PID parameters. So in fact the design process becomes rather complex. Okay, or the exact design, the determination of Kc, tau d and tau I now becomes much more complex than we had before, but at least we know that we can achieve zero steady state. Okay, so that's one of the kind of givens of the PID controller. Okay, so let me consider a simple case. Okay, so the question is, where should you put the zeros? Okay, so again, in fact, in terms of the selection of alpha and beta, again, root locus might be actually quite useful, even if we cannot determine exactly the locations of the zeros. We can at least speculate about their possible locations and the effects. Okay, so so I will consider one case, and I would urge you to also consider other cases and see for yourself that different possibilities exist, but some other possibilities are really not feasible at all. Okay, so remember that I had my original system having 2 poles at -1 and -2, and the PID controller introduces another pole at 0, and I would speculate that I can actually put 2 of the zeros over here, minus alpha and minus beta. Okay, way left on the real axis. Okay, you now at this point you have a feeling that it's often advantageous to put the zeros in the stable side of the S-plane, and in fact even further left than any existing poles, because what's going to happen is that because those zeros actually attract the branches of the root locus, eventually some of the branches will converge to these zeros, and that's a good thing, because any closed loop poles on the far from the j omega axis are actually relatively a more stable system. Okay, so let's apply our root locus knowledge here. Okay, so we will have basically how many branches we will have? Well, we will have 3 branches. Okay, and in terms of the asymptotes, because we have 3 poles, okay, so number of asymptotes is clearly n minus m is equal to 1, because we have 3 poles and 2 zeros. Okay, number of branches, clearly 3, is equal to maximum of m and n, and that is 3. And angle of asymptotes is clearly plus minus 180 degrees divided by the number of asymptotes, which is 1, 2L plus 1, so that gives us plus minus 180 degrees. So we only have one asymptote that is on the left real axis. Okay, so this region is part of the root locus, and we need to start from the poles. This region is part of the root locus, and I know that I need to start from the open loop pole and need to end up at the open loop 0. So clearly one of the branches is squeezed here, and the other branch is on the asymptote and needs to end at the 0, and we need to have a branch breakaway point here. And since I need to have these need to come back to the root locus, so these will basically go over here. Okay, why? Because there are 2 branches here, and one will need to go back to the 0, and the other one will need to go back to the to infinity at the asymptote. Okay, so obviously other possibilities exist. With different alpha beta locations and complex pair alpha beta. Okay, so that just gives you an idea about what happens with the PID controller. Essentially, we can make the steady state error 0, and also we can achieve pretty good root locus performance, because if you take a look at this, this is very similar to the PD controller performance, with the added benefit of 0 steady state error. Okay, you can see that this thing can achieve over here. Okay, so where is the best steady state error here? The best steady state error actually is achieved over here, right? So somewhere here. Okay, best TS, not over here. Okay, why? Because here we have a dominant pole which is squeezed between minus alpha and minus 2. So the best steady state error depends on the choice of minus alpha, and also is achieved at, remember, this point is where k goes to infinity. So in fact, this settling time becomes better and better as you increase the gain. All right. All right. Now I want to wrap this PID controller issue, or at least with the root locus, with some discussion on what kind of properties we have. Okay, so I'm going to call this practical considerations about the PID controller. Okay, and I will start with some notes about, let's say, notes about integral control. In fact, we have discussed other issues with derivative control, but I'm going to restate those as well. Okay, so first of all, it's very popular in the industry. Okay, but in PI form, okay, PI control form, we discussed the reason for that. Integral control by itself, in fact, is not very desirable, although it makes the steady state error for a unit step response of a type 0 system go to 0. The presence of the integrator actually makes the system less stable. So it really narrows down the stable region. But when you introduce the proportional control as well, you basically make that slightly better, okay? Because of the ability to make ESS equals 0 with self-regulating slash non-integrating slash type 0 systems. Okay, so remember, a self-regulating system is a type 0 system because it basically converges to a steady state value by itself. Okay, we have also seen that a combination, sorry, my tablet is trying to move away from me. Combination of P and I actions may achieve practical stability with and ESS equals 0 property. Remember, the integral control does not automatically make ESS equal to 0 for all systems. It really depends on the type of the original system, okay? But if your original system is type 0, then the integral control increases the type by 1. And if the system is type 0, so the new one becomes type 1, and type 1 system has 0 steady state error for a unit step input. If you apply a unit ramp input, you will get constant steady state error.
Hocam bir şey sorabilir miyim?
Shoot.
Tamam. Efendim? Şey diyecektim.
Söyleyin yani.
Doğalında bir derivatif term bulunduran plant gerçekte var mı? Yani plantte S diye bir terim var. Yani mesela integrator kullanmamıza rağmen şey olmuyor, ESS 0 olmuyor gibi bir ihtimal var mı? Pratikte en azından.
Tek başına S diye numerator'da bir S görmedim hiç. Ama yani bir araştırın. İlginç bir soru. Yani tek başına bir derivatif neden olmasın? Yani sonuçta aslında olabilir diye düşünüyorum.
Bakayım ben.
Sonuçta bir hani düşünürseniz time domain'de bir derivatifle bir integrator'ı peş peşe getirdiğiniz zaman normalde unity transfer function elde etmeniz lazım. An additional property is that it suffers from an effect called integral wind up, and I'm going to discuss this a bit further. Okay, this is a disadvantage of the integral term in the PID controller. Okay, so let me kind of discuss what that is. So the integral windup is an artifact of the integrator being actually a summation operation. Okay, remember that the integral basically takes the integral of the error function. Okay, so remember, for example, in PI control, okay, so controller output U of t is actually a bias term, a operating point term, plus Kc E of t, which is the proportional term, plus Kc over tau I, integral from 0 to t of E of tau d tau. Okay, so it's the integral of the error. Now, in practice, this has kind of a adverse effect. Okay, so consider what happens if your actuator is not ideal, but it can actually saturate. Okay, so think about a system where you have an error, and in order to diminish the error, you increase your output, your controller output, so your actuator output. But unfortunately, before being able to diminish the error further, the actuator saturates. For example, you have a motor which has a torque limit, and you need to apply a torque that is larger than the torque that the motor can apply. So the motor achieves its maximum torque, but it cannot go any further. If it cannot actually achieve the desired torque, the error will not diminish to zero anymore. You will have a constant error that's not diminishing, going away. So what's going to happen is that the integral term will keep accumulating that error and will accumulate a large sum as part of the integral term. Okay? So that's going to have an effect when the reference input changes. Let's say the reference input was desiring a certain torque, but then the reference input changes sign, and then you no longer need that torque. You need to diminish the required torque. So what happens is that the error becomes negative, but unfortunately your input will not change, will stay constant because of this large term. The input will remain saturated, okay? Because of this large term, it's going to take a while that the negative error will take this large sum below a certain value that is the actuator saturation value. Okay, so I'm going to try to illustrate this and then write that down. Okay, so here is your reference. Okay, so as soon as your reference changes sign, and let's say this is your output. This is your U of t, the actuator. So as your reference changes sign, it becomes a certain value, y desired. The input starts going up, so as the output will start going up. But then let's say this is your saturation value, U max. You cannot go beyond this value. So your actuator saturates. So what happens is that your output will no longer be able to close the gap in the error. Okay, so this output will also saturate. So and you will have basically an error here, E of t is equal to constant. Even if it's not constant, it's not gonna diminish anymore because you are not able to supply the required input. Okay, so what happens is that error is accumulated by the integral term. Let's say that the reference input changes sign here. It goes back to zero. So what happens is that the error here, the actual error becomes negative. Okay. But actually, what happens is that even if this term becomes negative now, unfortunately, this cumulative term cannot change sign or go below U max immediately. So what happens is that this, unfortunately, this input will remain saturated for a while until the integral term actually goes below that threshold value. And unfortunately, because the input is saturated, the error will not diminish for a while. And then once this function goes down, so will the output will start going down. Okay, so this region over here, no action from PID controller or PI controller for, or let's say because of this so-called integral windup. Okay, so let me write that down for you, the effect in practice. If the actuator saturates before E of t is equal to 0, error will stay non-zero with the same sign, I term, the integral term, will keep increasing, effectively keeping U of t saturated. When the desired output or the reference changes and E of t changes sign, the actuator will remain saturated and therefore will not respond immediately before I term falls below a certain value. Okay, so this is the description of the problem. So what kind of fixes there are in order to deal with that? These are known as, let's say, these have different names. They are known as anti-wind-up. These are terms that you will hear in the controller literature, or reset wind-up. So the wind-up is the effect, and anti-wind-up, reset wind-up, these are solutions for that problem. Okay, there can be multiple solutions. You can, for example, turn off. These solutions are not mathematical solutions, they are really procedural solutions. Okay, you need to somehow manage the different terms in the PID controller, in particular the integral term. Okay, so for example, just give me a second. You can turn off integration when U of t saturates, or you can again turn off integration whenever the controller is switched off. So if you disconnect the controller from the system, you need to prevent, the numerical algorithm to keep running, essentially accumulating this integral term. Okay, this is particularly important when you have a set of controllers and you switch on and off different controllers. So this is especially important in something called controller scheduling. Controller scheduling. Yes, go ahead.
Ya hocam ben şey diyecektim, bir yukarı çıkabilir.
Tabii ki.
Burada şey dedik ya, hani input ilk artıyor, işte y desired'a gidiyor umax. Sonra umax durduğu zaman y da duruyor da hani error'a...
Şöyle, y durmak zorunda değil. Yani anında, yani input durdu diye y duracak diye bir şey yok. Çünkü sistemin kendi bir dinamiği var. Ama şöyle düşünmelisiniz. Sonuçta error'ü sıfıra götürecek olan input'u ben veremiyorum. Yani şey gibi düşünebilirsiniz. Önünüzde bir araba var. Belli bir hızla gidiyor. Siz ona yetişmeye çalışıyorsunuz. Öndeki araba hızlanıyor. Siz de gaza basıyorsunuz ama gaz pedalı dibe dayandı. Arabanız daha hızlı gitmiyor. O zaman öndeki arabayla olan mesafeyi ya kapatamayacaksınız veya o mesafe giderek açılacak. Öyle düşünün.
Ben şeyi anlamamıştım sadece, işte umax durduğu zaman neden şeyde duruyor? Zaten umax durduğu zaman verdiğimiz u durursa şeyde olmaz mı? Y desired'da hani o alt kademeye düşmez mi?
Şöyle, o anda durmak zorunda değil ama bir yerde saturate olacaktır ve error'ü kapatamadan saturate olacaktır.
Yani o umax'ı verseydik ne alırdık dediğim şey y desired.
Aynen öyle. Yani şey gibi düşüneceksiniz. Hani sistemin de sonuçta plant'in de bir step response'u var ya. Sonuçta sisteme Umax'la bir step input uygulasaydınız sistem bir yere saturate olacaktı, değil mi? Öyle düşünün. Yani bir sisteme step input uyguladığınızda sistem o anda final değerinde bitmiyor yani. Arada bir dinamik var. Yumuşak bir biçimde o değere saturate olup kalıyor, değil mi? Ya
Peki,
bu şekilde.
Bu integral neden bunu sağlıyor? Mesela KCET dedik ya.
Evet.
O KCET işte error olduğu zaman error dursa bile negatif falan olabilir dediniz. Diğer taraf hep pozitif oluyor dediniz. Nasıl negatif oluyor?
Şimdi şöyle, şimdi düşünürseniz, yani şuraya bakarsanız, şimdi şurada error pozitif. Mesela burada error pozitif. Diyelim ki şurada da error negatif. Tamam mı? Şimdi error negatif olduğu anda şu terim anında negatife geçiyor. Hiçbir sıkıntı yok. Yani sadece bu terim olsaydı u of t anında değer değiştirecekti. İşaret değiştirecekti. Doğru mu? Fakat şuradaki terim historisi olan bir terim. Yani anlık tepki veren bir terim değil. Bu bir toplam terimi. Siz burada uzun süre pozitif bir sayıyı toplarsanız e of t negatife geçtiği zaman uzun bir süre çıkarmak zorunda kalırsınız. Anlatabiliyor muyum?
Anladım.
Ne demek istediğimi anlatabiliyorum. Yani bu integral terimi anında tepki veren bir terim değil. Çünkü bu eğer belli bir miktar toplandıysa, u of t kocaman bir değer yaptıysa, u max'ın üzerinde bir terim. O zaman e of t işaret değiştirdiğinde de siz u max'ın altına ininceye kadar bu toplam çıkarmaya devam etmek zorundasınız o toplamdan. Dolayısıyla belli bir süre input, daha doğrusu actuator saturated kalacak. Çünkü neden? Evet, u değeri, gerçek u değeri azalmaya başlayacak ama u max'ın üzerinde kalacak bir süre daha.
Anladım.
Tamam. Başka soru var mı? Alright. So that is an important property of the integral controller, a practical property, because if you think about 302, we never talked about actuator saturation, any practical issues like that, okay? But in practice, any actuator anything that your controller drives actually has a physical limitation. So you can supply certain numbers to the actuator, but it really depends on what is achievable by the actuator. For example, if you think about a plane, an autopilot, okay, your wings, your control surfaces have certain angular ranges. If you reach that angular range, any input that you apply beyond that point will not be registered physically. Okay, so any time you have a limitation on the actuator, integral windup is a problem actually. Okay, so let me also reiterate some of the issues with the derivative controller. Okay, so we talked about notes about integral control. Now I want to talk about again notes about the derivative control. Derivative control. Okay. So in theory, derivative action adds stability to a system. Remember that it adds a zero to the system, and if you add the zero actually on the left half S-plane, on the left of existing poles, you can actually draw the whole root locus towards the zero, and therefore you can improve many properties of the system. Okay? So you will curbing overshoots and often improve settling time. Okay. In practice, however, derivative is not a very nice operation again. Okay. In practice, derivative operation have some drawbacks. Okay. One issue is the so-called derivative kick. Okay. So think about if your reference input, okay, if your R of t actually is piecewise constant, okay, the error will be piecewise constant. Okay, so your error function, let's call this E of t, it will also have a discontinuity. Okay, depending on what the output is, obviously, it's not going to have the same value. So what will happen is that your d E of t over dt will basically have a spike at this discontinuity. Okay, so that will result in your actuator function u of t also having basically a large spike at that point where you have this change in the reference signal. Okay, so let's say any sudden changes in R of t, hence in E of t, will result in numerical instability at u of t. What I mean by numerical instability is that you may end up with a very sudden large value change in the actuator function u of t. Okay, this will have basically adversely affects physical actuators. Let's say if this is a motor, you will suddenly inject a large amount of current to the motor. If this is a mechanical device, you will suddenly, jolt the device with a unnecessary large value. Okay. So the solution for that, solution to the derivative kick, often the derivative of the output y of t, in fact this is the measurement of the output, is used instead of the error E of t in the derivative term. Remember, we have discussed the fact that in fact E of t is equal to R of t minus Y of t, and dE of t over dt is equal to dr of t over dt minus dy of t over dt. So this if r of t for piecewise constant r of t, dr of t over dt is mostly equal to 0. Okay, it's non-zero only at finite instance of time. Okay, so therefore we can say that instead of dE of t over dt, it's like if we use minus dy of t over dt, okay, it's going to be mostly true, and in fact we would have eliminated these spiky dr of t over dt terms. Okay, the instantaneous non-zero terms are eliminated from the signal itself. So it's going to be equal to each other for almost everywhere in time, except at those very small instants of time where the reference changes. Okay, does not hold for arbitrary r of t. So if your r of t in fact is continuously changing, unfortunately you can't do that. But you can't do it, but also the problem itself is not actually apparent, because you don't have any sudden changes in r of t anymore. Okay. There is another issue. So let me see. So we said derivative kick, one issue. Another issue is the high pass effect of the derivative. Okay. If you remember your Bode plots tells us that derivative, which is a standalone S term, okay, but it can also be just a zero, actually, S term, or a zero, S term or a zero, has a high pass characteristic. What is a high pass characteristic? Let me show you an example. Let's say example. So if your GC of S is actually KD times S plus alpha, where you have a derivative operation, if you sketch the Bode plot of this, you will see that there will be a corner frequency at 1 over alpha. So you will have basically a Bode plot coming like this, the asymptote. And then at this point, the asymptote will start increasing with 20 dB per decade. Okay? So the actual response will look something like this. Okay? In the log scale, 20 log GC of S. So you see that this exponentially amplifies high frequencies. Okay, this is what we mean by a high pass effect, and if you guys are taking 430, you will also use that terminology, the filtering terminology. So this is not a good thing, because if you have any existing noise in your measurements, let's say you are measuring y of t and you have a constant reference, so any noise in measuring y of t will actually be apparent in the error function e of t as well. And when you take the derivative of e of t, what will happen is that any high frequency noise in e of t will get exponentially amplified. Okay, so any small amount of noise will become a very large amount of noise. Okay, so let me sketch that for you. So if you think about our controller residing here at its usual location, so this is our plant. Let's say this is y of t, and let's say I'm measuring y of t, but in here I have d of t, some high frequency noise. In fact, the noise does not need to be at high frequencies, it can be anywhere. It is enough that it has some components at the high frequency. Okay, so this goes in over here, R of t, E of t. So you see that this noise actually goes through GC of S, and therefore it just seeps as an amplified noise at the actuator. So the amplified noise in U of t can be a big problem in practice. Again, the effect is that you have a very a high frequency component in U of t, so that will just, you know, vibrate any actuator. There will be current fluctuations in your motor. Mechanically, system will wear down much faster, and so on. So what about solutions? One practical solution, and you will see this partly in EE406, the next term. Okay, if possible, one practical solution, if possible, measure directly the derivative, the derivative term instead of the original variable. I will make that clear in a minute. Original variable. Let's say you are originally measuring the position, but you need the velocity. Normally, if your measurement variable is the position, you will take the derivative of the position to compute velocity. But maybe you are able to measure velocity directly. Okay, you may have some sensor that directly measures the velocity. If that's the case, use the velocity directly rather than taking the derivative of the position variable. Okay, that has a name often. you can hear about something called the proportional velocity controller instead of proportional derivative controller. Okay, so that means instead of measuring x or theta and taking derivative, measure x dot or theta dot directly using a suitable sensor. The difference being, if you have any sensor noise, in this case the sensor noise will be added directly to the velocity variable rather than being added to the position variable and being amplified by the derivative operation. There is another solution, another solution, and you will see this often again. Another solution is to low pass filter y of t or e of t before feeding to the derivative action. That means before taking the derivative action. But this doesn't mean filter it for all operations. Just filter it before taking the derivative. Okay? All right. Any questions so far? Any questions? All right. So let's take a break. It is 10:33 right now. So after 10 minutes, we will meet here and I will immediately have your class exercise. So please don't be late. Okay? Is there any questions? All right.
Hocam, benim bir sorum var aslında.
Söyleyin.
Emin olamamıştım. Bu low pass kullanırsak hani derivatiften önce noise'u filtrelemek için R of T'yi de filtreleme ihtimali var mı öyle bir durum?
Şimdi E of T'yi filtrelediğinizde R of T'yi de filtrelemiş oluyorsunuz. Doğru. Ama unutmayın, sadece derivatif terimi için. Aslında derivatif teriminin kolaylaştırmış oluyorsunuz. Çünkü ani değişen bir R of T derivatifde zaten sorun çıkartıyordu hatırlarsanız. Ama bütün mesela PID controller'ın bütün terimlerine filtrelenmiş halini verirseniz o zaman sistemin responsunu damp etmiş olursunuz. Yani yavaşlatmış olursunuz. Yani her şeye o zaman bir low pass etki getirmiş oluyorsunuz. Burada sadece derivatif işleminin o high pass etkisini kompanse etmek için bir low pass filtre getiriyoruz. Dolayısıyla sadece derivatif terimi için bunu yapmış oluyoruz.
Sağ olun.
Peki arkadaşlar, görüşürüz o zaman. Çıkmıyorum ben. Siz de şey yapabilirsiniz, açık bırakabilirsiniz istiyorsanız.